Hi, my name is Petrovicheva, and I'm happy to present here at DevOps conference. I'd like to share my experience of applying machine learning processes to deep learning model development. I've been doing computer vision since 2011, and since then I worked at companies like Intel and developed libraries like OpenCV. OpenCV is the biggest computer vision library in the world. You can find it in every smartphone, as well as yours, and it's responsible for image and video processing. It's open source and is used by millions of people worldwide. So during my work, I implemented algorithms for many areas of human life, including autonomous driving, medical diagnosis, retail, artificial reality, sports, and other fields. And I would like to share my thoughts on how to make sure that the model development process is healthy. So today we'll cover why MLOps matters and why it's different from DevOps. I'll share best techniques on how to store and treat datasets, models, and metrics. And we'll also talk about engineering practices and tools to use in the process. So first, let's talk about what computer vision is. Computer vision is a family of algorithms that use some image or video as an input and recognize it in some way. For example, this algorithm here recognizes that this image has a cat. Why can't we just use DevOps practices in our processes? So we are people, we are computer programmers, and we write code to express our algorithms, our computer vision algorithms. But we also have models that kind of describe the algorithm itself. Model is the result of the training, and it's a binary file. We also have data sets, and this is a lot of images or videos that are used for training. In fact, it's even more complex. So we have several parts of code not necessarily related to each other. One is called training code, and the other is inference code. The training we use obviously for training, and inference part matters when we go into production. Model, as we said, it's a binary file. It can be up to 1 GB in size, so we definitely cannot put that into Git. And dataset also is split into parts. We have training, validation, and test part of it, and it can be up to 3 terabytes in memory size. Again, we cannot put that into Git. Okay, let's first discuss what happens when you develop the model. So obviously you write some code. It has several versions, and you can see these versions here on the left. So these are different commits of the code that describes our algorithm. Then on the right you can see datasets, and again we have several versions of the datasets. And then the combination of code and dataset may create something called model. In fact, every checkpoint, every commit of the code can create several versions of models. They would be different. It depends on how long did you train the model. Now, every model has a number called accuracy here, and you can see that one models are better than the others. And the best model we got is the second to last row here, that is in bold. And we would really like to memorize this combination, this nice lucky combination of the code and dataset that create these models and parameters of this model too. So we kind of need to store this all together. We cannot store the code separately from the dataset that created this nice checkpoint of the model here. Now, when we create these algorithms, we actually never start from scratch. We typically start with some public baselines, with some papers, with some code, and you can find these baselines on sites. For example, this site here is called Papers with Code, and it contains state-of-the-art, like trending research. Every paper here has a corresponding link to a GitHub repo. So typically the process goes like this. You find a new exciting paper that states that they have new state-of-the-art accuracy, for example 87% in some specific task. You get all excited, you go to you will really want to reproduce these results on your side. So you go to GitHub to download the code. You go to Google Drive to download the model and use some custom script finally to download the dataset. Now you change nothing. You just run the validation script from the repo and you get totally different accuracy on your side. So 76% in this example. It's definitely different from 87 that the author stated. And you try to understand what happened here. So you actually cannot reproduce the publicly stated result. So it seems like a bug, and it seems like a weird issue. But in practice, it is a very common scenario. In fact, 90% of the papers that I work with are not reproducible. So they have this scenario when I tried them the first time. Only 10% of the papers I worked with were nice and reproducible, which clearly states that there is something wrong with the field. In fact, deep learning field is very young and kind of doesn't have a really established process yet, hopefully. So DevOps people and machine learning ops people really would help the field to develop into something mature, stable, and really helping the community. So let's discuss the datasets. As we already discussed, dataset is a collection of images or videos, each of them having some tag or label or data to them. So here these tags are cat, dog, and fish. So these datasets actually need to be very big. So something meaningful starts with 10,000 of images, and they can be up to tens of millions of images in a dataset. The main reason why the dataset needs to be big is for it to be diverse. So imagine that we want to classify these cats in real life, right? In this case, we would really want our dataset to have all the different examples of different breeds, colors, sizes, ages, whatever environments for the cats. So to make sure that our model is prepared for the real life scenarios. So when I say diverse data here, I don't necessarily mean diverse in terms of like people's skin color, but this also can be an example of diversity. So there is an application called FaceUp. It's a pretty popular application actually. It can apply some nice filters to your face, for example, make you smile, look younger or older, and also it has a filter called hot. So this hot filter kind of makes people look better in some sense. The network was trained on some data set to do that. They have neural network inside. So the problem here is that their data set was not representative enough, and it clearly didn't have enough hot people of darker skin color. So the network kind of automatically assumed that hot means white. And when you use this application on photos of people with darker skin color, it typically made them whiter to make them look hotter. There was a huge scandal based on this a couple of years ago. And this scandal, the pure reason of this scandal was not diverse enough data set used for machine learning model training. Okay. So these data sets, they also have data annotation, as we discussed. These labels that are attached to these images. So these annotations are actually produced by humans and human annotators. So it's actually a huge work to annotate a data set, which means that if you have an annotation team and you want to get your dataset annotated, it will take some time for them. And you typically get your dataset annotated in chunks. So for example, first half of data may be annotated on day 10, and dataset can get fully annotated on day 20. So you are eager to start training something, so it's totally possible that already on day 10, the team already starts training something. And this means that you need to remember different versions of the data. These different versions of the data may also come from different reasons, from continuous like data annotation process, but also some filtering, adding or removing some images, and stuff like that. So if you don't keep track of your data, you may actually find yourself with something like these. And I wouldn't really say that this is kind of a rare case. I actually saw that happening in real life. In this case, when you don't have your data structured at all, it means that you most probably don't know what was the data set you trained your model on. How different are these data sets? And finally, your disk space you may run out of your disk space if you store each and every small version of this data. Why do you actually need to compare the versions of your data? Why do you need to version your data? This need comes from the fact that you cannot compare models trained on different versions of the data. So imagine that on day 10 you trained your model on half of the data, and then you trained the model on full data. It wouldn't be actually fair to compare them because the first model only saw a part of the data. So you actually need to remember what were the versions of the data. And then remember that we cannot put them into Git. So we need to come up with some scheme to get this data versioned. You may already notice that these kind of scattered folders with weird names really look like kind of pre-version control era, when there were like old folder with the code and new folder with some different changed code. So it clearly seems like we need some development operations processes here to version the data. Now, to version the data, you can use various schemes as long as they are consistent with themselves. For example, it's totally fine to go with version 1, version 2, whatever, as long as it's consistent. You may also go with a timestamp. For example, if you don't create your data sets more often than once a second, the second row will be totally fine with you. You can also use tools for that. Most commonly used tool for dataset storage is data version control, or DVC. And you just say DVC add dataset and you are done. Your dataset is stored in DVC storage in some structured way. Okay, so let's discuss the models. When speaking about models, we typically need to talk about the accuracy of the models. The accuracy is kind of the quality of the model. For example, here we see that the model got 2 out of 3 images correctly, which means that its accuracy is about 67%. Now, the main task of data scientists who create models is to make the accuracy higher. To do that, they typically start with some baseline, as we discussed, and then iteratively apply some new features on top of that. And the final solution typically looks like this. So we stack features on top of the model. There can be up to 20 features applied like this way. Now, to find these 20 features that really improve the quality of the model, you typically need to do some hundreds of experiments. And you need to remember which experiments were good and productive, which experiments improved the model, and which didn't, and more importantly, which made the model worse. To do that, you need to keep track of your experiments, and you also need to make sure that the model experiments are reproducible. Okay, so I will talk about some very obvious things for DevOps conference, but they are not so obvious in deep learning community so far. So every experiment that researchers do needs to correspond a single specific commit of the code. Well, people need to commit the code, right? So it's actually very common to run experiments from uncommitted code, then change it, and never be able to reproduce the experiment some good results that were achieved with this experiment. To make sure this never happens, every experiment should correspond to some specific committed version of the code, and this code should have everything needed to reproduce these results, including some parameters, paths, and other flags that you typically can pass as a parameter of the Python script. So these parameters ideally need to be stored along with the code in some format like JSON. Okay, so let's discuss best engineering practices. One of the main things I would recommend is to think early about the integration. Now, typically in big teams, machine learning people do models, and then integration to the real-life solution is done by some other people. Which means that in machine learning, it's pretty common to not have good processes, not have tests, continuous integration, and all these good things that are provided by DevOps community and culture. Now, I believe that this is very important to have in any process, including machine learning model development, because there are some models that cannot be integrated in real-life solution. And it would be really hard to integrate model into real-life solution if it wasn't properly tested in the process for some key features that, for example, you have in your target software. So it's really not common in machine learning and deep learning community to write tests. I totally understand that this is a surprising thing for DevOps conference, but yeah, so I only saw a few projects that have validation tests for their machine learning models, and I probably never saw models that were tested in the training stage. But if you do something that would go into production, you need to test your models on every stage of the development process. Because of this, I totally recommend to implement the tests. So at least integration tests for training would be helpful in the development stage, and definitely you need good tests for validation of the models. So we also do not use IPython notebooks. In machine learning world, there is a very popular tool called IPython notebooks that are absolutely great for prototyping, for fast experimentation. They are very visual and nice to play with. The problem is they are very hard to integrate, almost impossible. Only a few companies do have them in production, which still surprises me a lot. I would expect that no one would have it. So IPython notebooks are really hard to test, they are hard to reproduce, and they are very bad for integration. So in my team, we decided to never use them. We only use Python scripts that are testable and easy to put into CI. Okay, so let's speak about the tools. I would say it's something very surprising for a DevOps conference. I would recommend to use Docker. Yeah, I totally understand that for DevOps culture, this is a totally like accepted thing everywhere. But for machine learning world, it's not there yet. So not a lot of people use it for training or integration stage. To be honest, for training, Docker is absolutely great for cloud training solutions. For example, when you train in AWS or Azure environments, it works perfectly for these scenarios. I myself and my team, we prefer to train locally. So I myself have a huge warm computer standing on my desktop with 2 GPUs, and I train locally. And for this, Docker may be an overkill. You can just train with a virtual environment that is kind of an isolated system, doesn't have any external packages in that, and you can reproduce that for different machines. For inference, shipping, and obviously for continuous integration, Docker is an absolute must. So we use it everywhere, and I totally recommend to other machine learning teams and machine learning operations people to extensively use Docker in their processes. Now, we already discussed dataset versioning, but we also need to version the models. And for that, we again can use a data version control tool. That is again a widely accepted tool for model versioning too. We can also use GitLFS for both, actually. Compared to DVC, GitLFS is not that convenient because DVC was created specifically for machine learning operations and machine learning people. There is one more area when we need visual and graphic tools. That is when we want to track how our model trains and compare it how it trains versus other models, my models or models of other people in my team. For that, you need some visual graphic tool to make sure that your models converges smoothly and doesn't diverge. So there is a bunch of tools for that. Some of them are TensorBoard, Secretboard, and weights and biases. They're kind of different in their scenarios. For example, TensorBoard and Secretboard are local tools, and weights and biases is a remote tool. So you actually look at your plots at some website page in your account, and you can compare and collaborate with people all over the world like that. The only downside of that is that when you don't have internet on your computer, it would be hard for you to track how your model trains. Okay, so let me summarize. I definitely recommend you to track your experiments and your data when you work with the model development process. And most importantly, I definitely recommend to care early about the integration when you develop these models, because you really want to make sure that you don't only create some nice research concept model, but to make sure that your model goes into real life and helps real people. Thank you.